So, I had already initiated the discussion on the conditional probability in my last lecture. You can see what I will recapitulate. If I am considering say tossing of a fair die and I consider the event A as 1 occurs, then what is the probability of it? It is 1 by 6. Now, I modify my statement. What is the probability that 1 occurs given that an odd number occurs, and I call it probability of A given that B has occurred. Now, out of these 6 possible outcomes in the fair die, there are 3 outcomes which are odd numbers 1, 3 and 5. So, now out of this if I say what is the probability that 1 has occurred, then it will be 1 by 3. So, this is actually leading to the concept of conditional probability. That means, if I have additional knowledge of certain event in an experiment, then my original probability may get modified. So, let us define, let A and B be any two events where the probability of B is positive. Okay. Then the conditional probability of A given that event B has occurred So, this is defined in the following fashion. We write this notation: probability of A conditioned on B. So, it is read as probability of A given B. Okay. It is defined to be probability of A intersection B divided by probability of B. If I apply this formula to this particular case, so you can see probability of A intersection B. So, A is 1 occurs and B is 135. So, A intersection B is 1. So, it will become 1 by 6 and probability of B is half. So, 1 by 6 divided by 1 by 2, that will give me 1 by 3. So, this definition is conforming to this original understanding of what is conditional probability. So, let me extend this argument little bit. Let me call this relation number 1. From relation 1, we can write probability of A intersection B is equal to probability of B into probability of A given B. Similarly, if probability of A is positive, then we can define probability of B given A also. So, that will become probability of B intersection A, which is same as A intersection B divided by probability of A. So, this will lead to the statement probability of A intersection B is equal to probability of A into probability of B given A. Let us look at these statements 2 and statements 3. And let us talk in terms of probabilistic interpretation. Statement number 2, on the left hand side I have probability of simultaneous occurrence of two events A and B. So, I am saying it is equal to probability of one of the events multiplied by probability of second event given the first event. So, the simultaneous occurrence probability can be calculated as a product of two probabilities One is conditional and another is probability of one of the events, which is also called marginal probability. And in this statement, the roles of A and B have been interchanged. These rules 1 and this 2 and 3, these are called multiplication rules. So, the basic concept of multiplication rule is that probability of simultaneous occurrence of two events can be calculated as a product of two probabilities. So, multiplication is there. So, that is why it is called a multiplication rule. Now, immediately the idea comes that can I extend it to 3 events? The answer is yes. In fact, I can write this multiplication rule for n number of events, and the proof is again by induction, as you have seen in the case of addition rule. So, let me give that now, the general multiplication rule. So, let us consider say a 1, a 2, a n be events, and in order to define the conditional probability, the event which is occurring in the denominator, that is like in the denominator I put probability of A or probability of B, then their probabilities must be positive, otherwise the ratio will not be defined. Therefore, I can put a condition probability of say intersection of I is equal to 1 to n is positive. Now, this actually condition is enough to say that probability of A 1 will be positive, probability of A 2 will be positive, or probability of A n will be positive, because this set is actually the smallest set. When I consider several events and I take intersection of all of them, then that is the smallest set. So, if I put the intersection of the smallest set to be having a positive probability, then all of the corresponding events, that means which will be occurring as individuals, or if they are occurring as taking intersecting 2 at a time, like A 1 intersection A 2, A 3 intersection A 4 etcetera, or taking intersection 3 at a time, all of them will have positive probabilities. So, let me just write here comment, this will ensure that all conditional probabilities are well defined. So, the general addition rule is multiplication rule is the probability of intersection I is equal to 1 to n, that is equal to probability of A 1 into probability of A 2 given A 1 into probability of A 3 given A 1 intersection A 2 and so on, probability of A n given A I is equal to 1 to n minus 1. So, this is the general multiplication rule. The proof is again using the principle of mathematical induction. Suppose I call this equation number 4, the relation 4 can be proved using the principle of mathematical induction. So, for example, I can say for n is equal to 1, the statement is always true, as it reduces to the left hand side for n is equal to 1, it will give me only one term, that is probability of A 1. Similarly, the right hand side also, when n is equal to 1 will have only one term. So, this statement is probability of A 1 is equal to probability of A 1. Now, assume it to be true for n is equal to k, then for n is equal to k plus 1, the statement is like this: probability of intersection A I is equal to 1 to k plus 1. So, firstly I consider it for splitting into two parts, A 1 intersection A 2 intersection A j, j is equal to 3 to k plus 1. So, this is becoming probability of A 1 intersection A 2 into probability of A j intersection A j, j is equal to 3 to k plus 1 given A 1 intersection A 2. Now, here I can again apply for n is equal to k. So, this can be further expanded and this I can write as probability of A 1 into probability of A 2 given A 1 and so on. Let me consider one example here. Let A be the event that a person gets cured from a disease, and B is the event that person gets some treatment, some medical treatment. Suppose I am assuming that the probability of B is 0.9, that is 90% of the people have access to the medical treatment which are suffering from this disease, and 80% of the persons who actually get the treatment get cured. Then what is the probability of A intersection B? Then it is equal to probability of B into probability of A given B, that is 0.9 into 0.8, that means 0.72. So, you can give the statement that 72% of the persons who get the disease actually get cured, because 90% of the people have access to the medical treatment, and out of the people who actually get the treatment 80% get cured. So, overall 72% people actually get cured. So, this is a direct application of the multiplication rule here. Now, this multiplication rule and the conditional probability concept is useful to consider calculation of probabilities where a certain event may arise out of several things. So, this is called something like a cause effect relationship. So, for a particular effect there can be several causes. So, for example, a person dying. So, the cause of death can be due to disease, due to accident or due to natural causes, etc. So, when we are calculating probability of the final effect, we may have to take into account various causes. So, each of the causes. Now, in probability this concept has been formalized by the concept of total probability. So, let me give this here: theorem of total probability. Let B 1, B 2, let me write a finite number of events, be pairwise disjoint and exhaustive events. Such that probability of B I is positive for all I. Okay. This is the notation for that, for each of the I, that is probability of B 1 is positive, probability of B 2 is positive, probability of B n is positive. Then for any event A, probability of A can be written as probability of A given B 1 into probability of B 1 plus probability of A given B 2 into probability of B 2 and so on, A given B n into probability of B n. Let us look at the proof of this. So, we have here exhaustive events, that means S is equal to union of B I is equal to 1 to n, where S is the sample space. So, we can write then A as A intersection S. Why? Because any event will be a subset of sample space. So, if I take A intersection S, I will get only A. Now, the advantage of this is that I can write S as union of B I is equal to 1 to n. Now, this is intersection union. So, I can apply the distributive law. So, the distributive law will give me union of I is equal to 1 to n A intersection B I. Now, you see what I have done. There is an event A which I have expressed as union of certain sets, and what type of sets. So, let us look at this also. I have assumed here that B 1, B 2 etcetera, they are disjoint sets. So, let us consider an rough diagram here. Suppose this is my sample space, okay, and I have event, say this is say my event B 1, this is event say B 2, this is event say B 3 and so on, and say suppose this is event B n. So, I have intentionally designed in such a way that these are disjoint as well as the union of all of them is actually equal to S. Now, A is any event here, okay. So, A is some event. So, what will happen to A intersection B 1? A intersection B 1 is this, A intersection B 2 is this dotted part, A intersection B 3 is say let me draw this curly lines here, A intersection B n is say, suppose I put here rounded figures here, okay. So, this is A intersection sorry, this part will be A intersection B n, not this. Now, you see if B 1, B 2, B 3, B n etcetera, they are disjoint, then A intersection B 1, A intersection B 2, A intersection B 3, A intersection B n are also disjoint. Since B 1, B 2, B n, they are pairwise disjoint, the sets or events A intersection B 1, A intersection B 2 and so on, A intersection B n will also be pairwise disjoint, because they are actually A intersection B 1 is actually a subset of, see this is a subset of B 1, A intersection B 2 is a subset of B 2 and so on, A intersection B n is a subset of B n. So, if this B 1, B 2, B n etcetera are disjoint, then A intersection B 1, A intersection B 2, A intersection B n will also be disjoint. Now, what we have done? A has been written as a union of disjoint events. If these are disjoint, then by the first I have given you the axiom of additivity, that is the Kolmogorov's axiom. There the third axiom was that if you have pairwise disjoint events, then the probability of the union is equal to sum of the probabilities. So, if I apply that by the axiom of additivity, we get probability of A is equal to probability of union A intersection B I is equal to 1 to n, that is equal to summation I is equal to 1 to n probability of A intersection B I. Now, this A intersection B I, again I can apply the multiplication rule on this. So, I will get it as summation I is equal to 1 to n probability of A given B I into probability of B I, which was actually the original statement of the theorem of total probability. That is, the probability of A is probability of A given B 1 into probability of B 1 plus probability of A given B 2 into probability of B 2 and so on, probability of A given B n into probability of B n. So, that statement we have proved here. To look at it into the context, actually it means that if a event can be decomposed as a union of n mutually exclusive events, then the probability of the final event is in terms of conditional probabilities of given each of them and the marginal probability of each of those events. So, let me give one example here. A fair coin is tossed once. If a head comes up, a fair die is tossed once, and if a tail comes up, a fair die is tossed twice. We want to find the probability that at least a 6 is observed. Okay, so, let us apply the theorem of total probability here, because there are two possibilities. You can have a head or you can have tail. So, if I consider the event, let H denote the event that head comes up, and say T denotes the event that tail comes up. That means, when a coin is tossed, then you may get a head or a tail, and I use this notation H and T for denoting that, and A is the event that a 6 is observed. So, then probability of A can be written as probability of A given H into probability of H plus probability of A given T into probability of T, because H union T is the full sample space here. So, you are able to get, you can say, the theorem of total probability here by splitting into events H and T. Now, let us look at the probability here. If a head is observed, then the consequence is that a die is tossed once. So, die is tossed once, what is the probability of head here? What is the probability of a 6? That will become 1 by 6. And what is the probability of a head here? That is half here, because it is a fair coin. In the second part, a tail comes, then a fair die is tossed twice. What is the probability of at least a 6? So, this I can calculate using that there is no 6. So, no 6 becomes, in one toss, probability that we do not get a 6, the probability will be 5 by 6. Now, 2 times it is done and both the times I do not get a 6, then the probability will be 5 by 6 is square. So, if I take 1 minus that, this is meaning that we get at least 1 6 and the probability of a tail is half. Now, this we can easily simplify and we get 17 by 72. So, you are getting, and let us also try to numerically interpret it. 17 by 72 is you can say little bit higher than 0.5. Sorry, it is little bit higher than 14 by 70, that is 0.2. When you have toss of a die, you have the probability of a 6 as 1 by 6. Okay. So, that is roughly 16% here, but here you are getting much higher than that, 17 by 72. So, the reason is that we are also allowing the possibility of the fair die to be tossed twice. Therefore, the probability of getting a 6 has increased from 1 by 6 to 17 by 72. Actually, 1 by 6 is 12 by 72 and here you are getting 17 by 72. So, numerically you can see by adding additional die only in part we have added the probability here. This is an application of the theorem of total probability. Now, in the theorem of total probability, what we are doing is that when an event is there, in order to calculate the probability of that event, we are looking conditioning on several causes. So, as I mentioned to you, cause effect relationship kind of thing. Now, we can further extend this idea. Suppose the effect is available to you, that means you already observed something, and but we did not notice what was the cause, and then we go back and see whether we can calculate the probability of the original cause, what could have been the cause. So, if we do that, then we are looking at the probability in a reverse way, or you can say conditional probability with reverse conditioning. Here we have given the concept that probability of A given B 1, probability of A given B 2, etcetera. But if I know what is A, then what is the probability of B 1? So, that means I am calculating probability of B 1 given A, probability of B 2 given A, etcetera. So, this concept is formalized in the famous statement of Bayes theorem. It is named after Thomas Bayes and this book was published on 1763 after his death. But the statement continues and this Bayesian theory has become very popular now in the context of decision theory. In various rules of estimation, Bayes estimators are used, Bayesian tests are used. So, Bayesian decision rules are used in practice. So, let me give the statement here. So, let B 1, B 2, B n be any events. So, again we are taking disjoint events which are exhaustive and probability of each of them is positive. Let A be any event with probability of A positive. Then probability of say B r given A, that is probability of A given B r into probability of B r divided by sigma probability of A given B I into probability of B I is equal to 1 to n. This statement is the famous statement of the Bayes theorem. Let us look at the proof, and as again you can see, since we have actually restricted our attention to the set theoretic notations and the axiomatic approach, the proofs are actually very simple. So, probability of B r given A, this statement is true for r is equal to 1, 2 and n, that means for any event I can calculate it. So, we apply the definition of the conditional probability. So, it becomes probability of B r intersection A divided by probability of A, and on this if you look at the numerator, I can apply the multiplication rule in the reverse way. That means, I can write it as probability of A given B r into probability of B r. This is using multiplication rule. And in the denominator, this probability of A, I simply apply the theorem of total probability, because I am having the same conditions that the events are disjoint and exhaustive. Then for disjoint and exhaustive events, probability of A is equal to sigma probability of A given B I probability of B I. So, I can write that here in the denominator. Using theorem of total probability. So, actually the statement has been proved just in 2 steps here. One step I just wrote the definition of conditional probability. In the second step, in the numerator I applied the multiplication rule, and in the denominator I have applied the theorem of total probability. So, the Bayes theorem has been established here. So, let us just consider one simple application here. So, a say computer manufacturer procures chips from 3 suppliers, say B 1, B 2, B 3, in proportion say 2/5, 3/10 and say 3/10 respectively. So, out of his total procurement of chips for fixing in the computers, he purchases 2/5 proportion from B 1, 3/10 from B 2 and 3/10 from B 3. It is known from experience that 1% of chips from B 1 are defective, 5% from B 2 are defective and 10% from B3 are defective. Okay. So, a chip is randomly selected from the collection of the manufacturer. It is found to be defective. So, what is the probability that it was supplied by B 1? Now, you see here this is cause effect relationship, because the final effect whether the chip is defective or not can be caused by the supply of B 1, B 2 or B 3. Now, we know finally the effect that it is actually defective. So, we are looking at what was the cause, that means who caused it. So, that is whether it was B 1 or B 2 or B 3, what are the respective probabilities here. So, let us calculate it here. So, if we apply the Bayes theorem, then we will have what is the probability of. So, let me define the events here. Suppose I define the event A as chip is defective. So, what is the probability of A? The probability of A will be summation probability of A given B I into probability of B I is equal to 1 to 3, where B I denotes the event that the chip is supplied by B I manufacturer. So, here I know all these things, because probability of B 1 is known to me 2 by 5, probability of B 2 is 3 by 10, probability of B 3 is 3 by 10. Similarly, probability of A given B 1 is 1 by 100, probability of A given B 2 is 5 by 100, probability of A given B 3 is 10 by 100, because we know the probability of defective chips from each of the suppliers. So, if we substitute these values here, I get here 1 by 100 into 2 by 5 plus 5 by 100 into 3 by 10 plus 10 by 100 into 3 by 10. So, that is equal to, we can calculate this easily, that is equal to 0.049. You can also try to appreciate this number. That means, basically we are saying approximately 5% of the chips are defective, which the person procures, the manufacturer procures. See, he is procuring from 3, one of them has 1% defective, another has 5% defective and another has 10% defective. Now, he is taking in miscellaneous quantities from each of them. Overall, his collection will have nearly 0.49, that is, you can say nearly 5% defective chips. Now, if I want to calculate the probability of say B 1 given A, then by the Bayes theorem it is becoming probability of A given B 1 into probability of B 1 divided by probability of A. So, that is equal to 1 by 100 into 2 by 5 divided by 0.049. So, after simplification it turns out to be simply 4 by 49. Similarly, I can calculate probability of B 2 given A, that is equal to probability of A given B 2 into probability of B 2 divided by probability of A. So, that is equal to 5 by 100 into 3 by 10 divided by 0.049, that is equal to 15 by 49, and probability of B 3 given A is equal to probability of A given B 3 into probability of B 3 divided by probability of A, that is equal to 10 by 100 into 3 by 10 divided by 0.049, that is equal to 30 by 49. Let us see the effect of the numbers here. See what were the probabilities of B 1, that was 2 by 5, probability of B 2 was 3 by 10, the probability of B 3 was also 3 by 10. But the conditional probabilities now have become quite different. From 2 by 5, which is approximately 40%, it has gone down to 4 by 49, that is less than 10% actually, it has become less than 10%, whereas this number has appreciated from 3 by 10, it has become 15 by 49, and this number from 3 by 10, it has become 30 by 49, which is nearly 60%. What does it mean? Since we have observed the final effect, that means the chip is actually defective. So, which company is more likely to supply the defective chip? Because we are purchasing things from B 1, B 2 and B 3, and B 3 is having maximum number of defective, that is 10% defective chips are there. So, if the chip is defective, it is highly possible that it was supplied by B 3, because the almost 60% chance is that from B 3 that defective chip was supplied, and somewhat less chance from B 2, that is 5% defective. So, that has become now more than 5% here, and the share of B 1 has become much less, although we are taking 40% product from B 1, but since the number of defectives from B 1 is much less, that is 1% only. Therefore, if ultimately the chip is defective, the chances are less that it would have been supplied from B 1. So, basically this is the effect of the Bayes theorem, or you can say, because we are able to do the cause effect relationship in perspective. This can have applications in several areas, especially in crime detection, doing some forensic examination, etc., where we actually know the final thing and then we want to detect the causes. So, this particular result particularly became very famous, and currently it is being applied in various areas of science and engineering. Now, after this we have considered the concept of conditioning. That means, conditioning actually affects occurrence of the probability of occurrence of certain event. What if it does not affect? So, if it does not affect, we call it to be independent events. So, following from the conditioning, actually we can give a new concept, that is called independence of events. So, now we can say that if event B has no effect on the probability of occurrence of A, then it will mean that probability of A and probability of A given B must be same. So, if occurrence of B does not affect the probability of A, then this statement will be true, provided of course, this is well defined, that means, I am assuming that probability of B is positive. So, this statement you can write like this: probability of A intersection B divided by probability of B, that is equal to probability of A, which you can further write as probability of A intersection B is equal to probability of A into probability of B. Now, if you see this last statement, this is a symmetrical statement. In this statement, actually I am putting B as the conditioning event, but here there is no distinction between A and B, because I am simply saying probability of the simultaneous occurrence of A and B is equal to the product of the individual probabilities of A and B. In fact, if I consider another one, suppose I consider if occurrence of A does not affect the probability of B, then what will be the statement? The statement will be like this: probability of B given A is equal to probability of B. Again, if I simplify this, I can write it as probability of B intersection A divided by probability of A is equal to probability of B, which is again equal to, I take it to this side. So, it becomes probability of B intersection A is equal to probability of B into probability of A. So, if you look at event this is statement number 1 and statement number 2, these two statements are actually same, and the difference between this statement and this is that these statements are not symmetric. Here conditioning is on A, here conditioning is on B, but if you look at this final consequence, this statement is symmetric. So, we consider this as the definition of independence of two events. That means, we say events A and B are independent if this condition 1 is satisfied, because this will mean that occurrence of A does not affect occurrence of B, occurrence of B does not affect the occurrence of A. So, basically that should be the physical understanding of the concept of independence. So, we define like that. So, we define events A and B to be independent if probability of A intersection B is equal to probability of A into probability of B. So, let me give a very simple example. Suppose two fair dice are tossed simultaneously. Okay. And I consider the event, let A be the event that even number on the first die, and suppose I consider B to be the event even number on the second die. Okay. I want to check whether A and B are independent. So, what is the probability of A? See, if we look at the sample space when we toss two fair dice, then it is written like this. I will have numbers 1 1, 1 2 and so on, 1 6, 2 1, 2 2, 2 6 and so on. Finally, you will have 6 1, 6 2 and so on, 6 6. So, in how many of this there is an even number on the first die? So, if you look at the first die here, in the second row when 2 is occurring, then even number on the first. So, there are 6 such cases. Similarly, there will be 4 1, 4 2, 4 6, 6 1, 6 2, 6 6. That means, there are total 18 cases out of 36 cases where there is an even number on the first die. So, the probability of that becomes 18 by 36, that is equal to half. Similarly, if I consider what is the probability of B, that is an even number on the second die. So, if you look at the second die, the numbers, if you look at the second column here 1 2, 2 2 up to 6 2. So, here on the second die you have an even number. Similarly, if you have 1 4, 2 4 up to 6 4 or 1 6, 2 6, 6 6 etcetera, there is again 18 cases where you have an even number on the second die. So, the probability of that becomes half. Now, let us look at what is the probability of A intersection B. Now, A intersection B means that there is an even number on the first die and there is an even number on the second die. So, what are the cases? So, in the second row if you look at, you have 2 4, 2 2, 2 4 and 2 6. There are 3 cases in the second row. In the fourth row you will have 4 2, 4 4 and 4 6, and in the sixth row you have 6 2, 6 4 and 6 6. There are total 9 cases where you have an even number on the first die and an even number on the second die. So, the probability becomes 9 by 36, that is equal to 1 by 4. So, here you can easily observe that probability of A intersection B is equal to probability of A into probability of B. So, here you can say events A and B are independent. Events A and B, they are independent. Now, naturally you can think of extending the concept to more than 2 events. Now, naturally it comes out that if I consider 3 events, then what will be the conditions? Probability of A intersection B is the product of probability A and probability B. Probability of B intersection C, probability of A intersection C, but at the same time you have to take all the 3 also. So, if we define, we say events A, B, C are mutually independent if probability of A intersection B is equal to probability of A into probability of B, probability of B intersection C is equal to probability of B into probability of C, probability of C intersection A is equal to probability of C into probability of A, and probability of A intersection B intersection C is equal to probability of A into probability of B into probability of C. Actually, these 3 conditions, they are called conditions of pairwise independence, and if you take all the 4, then this is called mutually independent. In fact, there can be cases where out of these 4 conditions, maybe 3 conditions are satisfied or 2 conditions are satisfied. So, all the conditions may not be satisfied. In that case, we will not say that the events are independent. In the previous example, let C be the event that the sum is even. Okay. If we say the sum is even, then what are the possibilities here? What is the probability of C first of all? So, the sum is even in 1 1, 1 3, 1 5, 2 2, 2 4, 2 6, 3 1, 3 3, 3 5, 4 2, 4 4, 4 6, 5 1, 5 3, 5 5, 6 2, 6 4, 6 6. So, there are again total 18 cases. So, you will get probability of C is equal to half. If I consider probability of A intersection B, then that is the first one is even and the sum is even. if you consider that, then out of total 18 cases you will get only 9 cases, because you will get 2 2 2 4 2 6 etcetera, 4 2 4 4 4 6 6 2 6 4 6 6. So, the total 9 cases will be there. So, you will get 1 by 4 sorry A intersection C, because A intersection B we have already calculated. And if we consider probability of B intersection C, that is the second one is even and the sum is even, then it means the first one has to be even, then this becomes 9 by 36 again, the cases which I enumerated just now. So, A, B, C are pairwise independent. But if I look at what is the probability of A intersection B intersection C, that means all the three are true. Then all the three are true again in 9 cases only. So, this probability is also 1 by 4. So, it is not equal to probability of A into probability of B into probability of C. So, A, B, C are not mutually independent. In this particular example, I have considered 3 events where A, B, C, they are A and B are independent, B and C are independent, A and C are independent. But if I take all the 3 together, they are not independent. The reason is that if I take A and B, then C is automatically certified to be even, because if A is even, B is even, then C is dependent upon that. That is why this is not independent of A and B. In the next class, I will consider various problems on probability, various kind of applications of addition rule, multiplication rule, the theorem of total probability, Bayes theorem, and the concept of independence.